This is your presenter Asloop Mudassar, and I am presenting slide number 121 of the course on laser physics. Question is, describe the operation of a commercially available unidirectional ring resonator based on a non-planar ND-YAG laser cavity for producing single mode continuous wave laser operation, and which also provides an automatic control over the transverse mode operation without the use of additional selective elements such as birefringent filters and the Fabry-Perot etalons. The answer is a monolithic unidirectional single longitudinal mode ND-YAG laser based on ND-YAG crystal as a unidirectional ring resonator with non-planar cavity features is shown in figure number 1. So let me show you the figure first. This is figure 1. The caption of the figure is non-planar unidirectional ND-YAG ring laser cavity for achieving single longitudinal mode and single transverse mode operation. You can see that this is the input beam which will enter the interface, the front interface containing point A. So point A is being contained on the front interface, and the input beam, for example, from a semiconductor laser will be incident or will be entered into this anti-YAG ring laser cavity. So this light will propagate as in the direction of arrow and will hit the interface at which the point B is contained. So after hitting this interface containing point B, the light is reflected towards another face containing point C. And from the point C, the light is reflected towards the point D. And from the point D, the light is traveled back towards the front coupling optics that is shown by this arrow, and after passing through, for example, at point A, it emerges out from the output coupler. So this front face may be regarded as the output coupler. So the input beam enters at the output coupler, and of course the beam will also leave the output coupler, forming an output beam. So you see that there is also a magnetic field over here. So you see that the light will pass through main points, that is point A, point B, point C, point D, and then will come back towards point A and will exit the interface. So the input beam, this is the front interface, you see there, where you or you can say that it is a coupling interface in which the input beam is coupled and also the output beam is coupled out of this interface. So in the rest, you see that this is forming a ring laser, a ring cavity, ND-YAG. This is the ND-YAG crystal forming a ring resonator cavity. For example, because the light is turned back and the light forming a ring, you see, then will of course at point A it forms a ring that is from A to B, then B to C, then C to D, then D to A, and then of course the light ultimately exits the cavity. So we are going to give all the descriptions about this cavity. So let me read again. A monolithic unidirectional single longitudinal mode ND-YAG laser based on ND-YAG crystal as a unidirectional ring resonator with the non-planar cavity features is shown in figure number 1. So this is not a planar cavity, but it is a non-planar cavity. Non-planar cavity in the sense that the plane of incidence at point A is not the same as the plane of incidence at point B. So that's why it is called a non-planar cavity. It might be possible that the plane of incidence at point D is the same as the plane of incidence at point B, and the plane of incidence C also contained is also parallel, for example, to the plane of incidences at point B and D respectively. So in that sense, that the plane of incidence at point B makes some angle at the plane of incidence at point A. That's why we regard this cavity as a non-planar cavity. So the different surfaces of the Nd:YAG crystals are anti-reflection coated to make it a monolithic device capable of giving high frequency stability. Because this is a same part, a single crystal. That's why it ensures, because there are no relative parts of this crystal. All the parts are based on the same crystal structure. So that's why there would be a very high frequency stability of the beam which is obtained using such a cavity. The crystal as a resonator has four reflecting surfaces acting as mirrors. The front surface containing point A is a convex surface and is coated to make it partially reflecting and partially transmitting. So this front surface containing point A is a convex surface and it is a partially reflecting and partially transmitting, because the input beam is, for example, a beam coupled from semiconductor laser which will enter into this cavity, and then of course the Nd:YAG crystal will come out, Nd:YAG beam will come out from the path as shown inside the crystal, and of course will come out as an output beam. The path you see is shown over here. From the input beam, the path is shown towards B, towards C, towards D, and back to A, and then of course an exit beam is formed. The different surfaces of the Nd:YAG crystal are anti-reflection coated to make it a monolithic device capable of giving high frequency stability. The crystal as a resonator has four reflecting surfaces acting as mirrors. The front surface containing point A is a convex surface and it is coated to make it partially reflecting and partially transmitting. The rest of the surfaces totally internally reflect the incident beams. For example, the beam is totally internally reflected at point B. The beam is totally internally reflected from the interface containing point C, and the beam is totally internally reflected from the face containing point D. The planes of incidence at the faces B and D are at an angle, say R, to the plane of incidence at the plane of incidence at the face containing point A. So here the plane of incidence at point A and the plane of incidence at point B, they are at a relative angle with respect to each other. So we can say that the face, that is the plane of incidence at point B, makes an angle, for example, say capital R, with the plane of incidence at point A. And similarly, the plane of incidence through at point D also makes an angle, the same angle, that is angle R, with respect to the plane of incidence at point A. It means that the plane of incidence at the point B and at the point D are parallel to each other. The plane of incidence of the top face, for example, the plane BCD, is nearly normal to those of the corner faces. So the plane of incidence through point B, C, and D. The plane through point B, C, and D is actually perpendicular to the faces at point B and D. So it means that it is also parallel to the plane of incidences at point B and at point D. So the plane of incidence of the top face, that is plane BCD, is nearly normal to those of the corner faces. As the planes of incidence rotate by an angle r, the net polarization rotates by an angle 2r in one round trip. So you see that, as said earlier, that the plane of incidence at point B, C, and D are parallel, and all these planes are at an angle capital R with respect to the plane of incidence at point A. So the polarization is rotated at the polarization. So the angle, or as the plane of incidence rotates by an angle r, the net polarization rotates by an angle 2r in one round trip. So this crystal, this ND YAG, so this our ND YAG ring resonator is actually also acting as a polarization rotator. So it will rotate the polarization by an angle 2r. If capital R is the angle with the fast axis, for example, with the one of the fast axis of the crystal. The non-planarity, as I said, that the planes are non-linear in the sense that the plane of incidence at point B, C, and D are at an angle at an angle capital R with respect to the plane of incidence at point A. So so our ND-YAG crystal is a non-linear. The non-linearity of the ND-YAG crystal creates an effect equivalent to half wave plate. And you know that the purpose of the half of wave plate is actually to rotate the polarization state of the incident beam. And here, this is what our ND-YAG ring resonator does the job. It rotates the plane of polarization of the incident beam. And let me give you a brief discussion about the half wave plate. When the light enters a half wave plate, two beams are generated: the O beam, that is the ordinary beam, and the E beam, which is the extraordinary beam. When these two beams exit the half wave plate, there is a phase difference equal to pi between the two beams. And when these two beams combine, the state of polarization is rotated. And this rotation of a state of a polarization is twice the angle with which the input beam makes with the fast axis of the half wave plate crystal. Under the application of a constant magnetic field, so you see that we have applied a constant magnetic field over here along the longer dimensions of the crystal. That is, we have applied the magnetic field along the longer dimensions of the crystal, along the whole crystal. So this magnetic field, which is shown over here, is also penetrating through all the crystal, and also on the left of the crystal. You can also put this arrow on the left side of this crystal also. Under the application of a constant magnetic field along the longer dimension of the crystal, Faraday rotation takes place. And you know that the Faraday rotation also serves the purpose of rotating the state of a polarization of the incident beam. So when the beam with a state of polarization enters into the crystal, then in the presence of the magnetic field, which acts as a Faraday rotator, the polarization states of the electric field of the input field is rotated. So the Faraday rotation takes place when the light travels from A to B, and also it works when the beam travels from D to A. So the Faraday rotation will be in action when the light travels from A to B, and will also be in action when the light travels from B to A. The net rotation in one round trip will be equal to the difference in rotation due to non-planarity and due to the rotation due to magnetic field. So you see that in this crystal, in the presence of magnetic field, there are two ways of rotation of the polarization. One is one thing that is the responsibility for the rotation of the polarization state within the crystal, within the ND-YAG crystal, is the non-planarity of the crystal, and this rotates the polarization state. And the other factor that could rotate the polarization state is due to the application of the magnetic field, which gives rise to the Faraday rotation effect. So there are two possible reasons for the rotation. One will rotate clockwise, for example, the other will rotate anti-clockwise. Then we need to measure the net rotation, and the net rotation in one round trip will be equal to the difference in the rotation due to non-planarity and due to the rotation under the magnetic field. The anti-YAG slab is longitudinally pumped by a semiconductor laser. So here you can see that we have shown an input beam, but this input beam is a pump beam from a semiconductor laser. And this pump beam is pumping the anti-YAG crystal longitudinally, that is along the longer length. So along the longer length, the anti-YAG crystal is being pumped by the input beam or by the semiconductor beam, which is used as a pump beam. So the anti-YAG slab is longitudinally pumped by a semiconductor laser. When the incident beam is non-normal, that is the incident beam is making some angle with the normal, to the output coupler, that is the front face containing point A is also called the output coupler face. The P polarization is more strongly transmitted. The resonator is more strongly transmitted. The resonator then favors the oscillations of polarization modes close to S polarization. So you see that since our incident beam is non-normal at the output coupler, it means that the P polarization is strongly transmitted through the front face of the crystal or through the output coupler of the crystal, and the resonator then the resonator means the rest of the laser crystal structure then favors the oscillation of the polarization modes close to the S polarization. Birefringence due to total internal reflections at points B, C, and D force elliptical polarization. If the net rotation is close to zero, then a purely S polarization will oscillate and the output coupling is nullified. So this is very important point. You see that if the birefringence due to internal reflections at point B, C, and D force elliptical polarization, and if the net rotation is close to zero, then a purely S polarization state will oscillate and the output coupling is nullified. So you see that if the beam has an S state, S polarization states, it will not be it cannot exit through the output coupler, because the coupler maximizes the transmission when the P beam of the P polarization state is maximally transmitted. So if our beam within the crystal, so if our beam within the crystal has S state of a polarization, it will be nullified through the output coupler. That is, there will be no output due to S polarization states. In the presence of the magnetic field, oscillation is unidirectional, single mode, and stable. So you see that this is the advantage, that in the presence of the magnetic field, the oscillation is unidirectional, single mode, and stable. And you know that the unidirectional crystals always allow the single mode oscillations to take place. And of course, the cavity is highly stable because it is a monolithic cavity. It is a same structure, not different structures. In the absence of a magnetic field, the oscillation is bidirectional. So if there is no magnetic field, the oscillation could be bidirectional and multi-mode and extremely noisy. So you see that this output beam, which is coming from D to A, is also a part of this one, is also reflected backward. And then multiple oscillations could take place. And then of course multi-mode operations will be possible within the cavity if the magnetic field is not present. Because of the rotation, because the magnetic field, you know, that provides you a Faraday rotation, and the electric field and the polarization is rotated in such a way. If the magnetic field is not present, the polarization will not be rotated, will not be under the control, and of course any other state of a polarization coming of the beam coming from D to A will also be reflected back and will be supported for back reflection into the laser cavity. So it is the magnetic field that provides us the opportunity to control the magnetic field of the beam inside the cavity and allow unidirectional propagation. So in the absence of the magnetic field, the oscillation is bidirectional. Multi-mode, when it is bidirectional, then of course multi-mode is an evident feature and extremely noisy. No additional frequency selective elements such as birefringent filters or Fabry-Perot etalons are needed because the line width of the YAG is much smaller than that of the pumped laser, and that the longitudinal modes are well separated due to smaller cavity dimensions. So you see that there are two important features. Number one is that the cavity, this is the ND-YAG ring cavity. We cannot place any components within that cavity. So we cannot place any birefringent filters, or we cannot place any Fabry-Perot etalons inside the crystal, because the crystal is acting as a monolithic component. Besides that, we have two main features that is resulting from this crystal. One is that the line width of the anti-YAG laser is much smaller than that of the pumped laser. So our pumped laser being semiconductor has much broader line width, and the line width of the resulting beam from the anti-YAG crystal is very small. And the second point is that since crystal's dimension is very small, then of course the longitudinal modes are very well separated due to the smaller cavity dimensions. So since they are very well separated, the possibility is that any one only a single mode longitudinal model, single longitudinal mode operation will be possible. The focused beam, the focused pump beam has a transverse gain distribution that ensures an automatic operation of the single transverse mode. So you see that having a pumped laser with a specific transverse gain distribution, we can ensure an automatic operation of the single transverse mode. And what is the purpose of this transverse gain distribution of the input beam? The transverse gain distribution, which is that is what I am talking about, the pump beam. The transverse gain distribution of the pump beam refers to the spatial pattern of how the gain is distributed across the cross section of the laser medium or the beam. It helps to set up the required transverse modes of an oscillating beam. If the focused pump beam has a Gaussian transverse gain distribution, that is, if our semiconductor beam has a Gaussian transverse gain distribution, then the beam generated by the ND-YAG crystal will also be Gaussian. So it is the transverse gain distribution that actually determines the shape of the beam. So this is the end of slide number 121.